Okay, how to do a trie-tree, or it's sometimes referred to as a prefix tree. Before, and it's also known as some other things. I didn't put them up there. But before we get into this, I should mention that I am still a student going for my computer science degree or my computer science bachelor's degree. So I'm not a professional yet. And I started this series of tutorials mostly as a way for me to go back and reference things that I've learned in the past. As I move forward and I forget things, I thought this would be a nice easy way for me to go back and see how I did things. Let's get started. Trie tree, otherwise known as a prefix tree. So what is a trie tree? Well, let's get right into this. Like any tree, we start with a root. And what we're going to do is we're going to put words in our trie tree. It's mostly used so this way you can put in all the words in a document and you can search and see if a word exists, how many times it exists. When we put a word in our trie, we're going to do it character by character. So let's start with the word ABBA. And if you don't know what ABBA is, well then today you are in luck. I don't know if you can hear that, but if you can, oh yes, this is ABBA right here. Turn the music up. I don't want to put it too loud just in case. Oh, let's pause that right now, just in case it goes really crazy loud on the other end. So that was ABBA. So we're going to do this word. We're going to start with the first character, and since we started at our root, underneath our root would go the first character, A. Now our second character, B, which will be a child of A. Third character, B, which would be a child of B. And our last character, A, which is a child of B. And since A is the last node that makes up this entire word, we'll go ahead and put a subscript 1 right next to it, and we'll move on. So now let's do another word, abs, like stomach muscles, abs. So our first character, A, well, that already exists in our trie, so we'll move on to the next character, B. B is already there. Move on to the next character, S. So now there's S. So now B has two children. One is another B, and the other one is S. Since S is the last character in that word, we'll go ahead and put a subscript 1 and move on to the next word, cat. Well, C doesn't exist as a child of root for the first character, so we'll go ahead, we'll put C. Then A is a child of C, and T is a child of A. Now notice, even though A exists over here, this A is the first character in the word. This A exists as a child of C. This A exists as a child of root. So that's why multiple A's will be in multiple places. Now since T is the last character in the word, we'll go ahead and put a subscript 1. Move on to the next word, catch. So we'll start with C, that's already in there. We'll go ahead and move to the next character, A. A is already in the trie under C. To the next character, T. T already exists. Move on to the next character, another C. So C becomes a child of T. The next character, H, becomes a child of C. Since H is the last node that makes up this word, we'll go ahead and put a subscript 1. Move on to the next word. It's ABBA again. You know what that means. Alright, so there was Dancing Queen one more time. So now we have ABBA. So we'll go ahead, we'll do the first character, A, already in our trie, so we'll move on to the next character, B. B already exists under A. Next character, B, already exists under the other B. A already exists as a child of B. It is the last node, the last character in this word, so we'll go ahead and increment it from 1 to 2. And now we have 5 words. One word is in there twice. And if you notice, the height of the tree is the length of the longest word, which is what makes this very powerful. Because it doesn't matter how many words we can have. We can have 1,000,000 words, and the height of the tree will still only be the length of the longest word, which makes searching much faster. So that right there is, let me move this to the side so I can see this other screen. So that right there is visually what a trie is. So let's go into a little bit more programmably what is a trie. So we'll start with our root. And our root is a node. Our root contains a parent. The parent is a pointer to the node's parent node. So A, its parent would be root. C, its parent would be root. This A, its parent would be C. This A, its parent is root. So that's what parent is. It's a pointer to the root, or a pointer to the node that's its parent. Occurrences. How many times a word appears in the trie? Well, that's initially how I thought of it, but more specifically, it's how many times a specific node is the last node in a word. So this node right here, that's represented by S, it is the last node in only one word, ABS, abs. This T is the last node in cat. This H, the last node in catch. This A, ABBA is in there 2 times, so it's the last node in 2 words. It'll only have, the number would only be more than 1 if the same word is in the trie multiple times. And I should mention right now that there's multiple different ways to do this. When I first learned it, occurrences, it wasn't an integer that said how many times a word appears. It was actually a vector of integers, and you read in a document, and what the integer was the place of the word. So ABBA, if it was the 3rd word in there, then the first vector would be 3 because it would be the 3rd word, or 2 because 0, 1, 2, depending on how you did it. But I didn't need to do it that, or the way that we're doing it is just an integer of how many words. But I should mention that there's that other way, which I think is the more correct way for reading in a whole document. But we're just going to do just a few words, so we're doing it this way. Alright, now children. This is the fun part. So children is a pointer to an array that has a size equal to the size of the alphabet. So the alphabet I'm using is 26 characters, A through Z. So children will be a pointer to an array of size 26. The first element, element 0, would represent A, element 1 would represent B, and so on. And when you first make the children, all elements or all nodes in the array are set to null. And then once you have something to put in there, like right here, A, the first node, well then element 0 would no longer be null because you've put a node in there. And we're going to show we're going to represent all this right now on the screen. So we have our node, and first thing we're going to do is set parent. So we're going to set parent to null because we don't know what the parent is yet. Occurrences, well, we haven't reached the end of a word. Occurrences will be initially set to 0. And children would be an array of size 26, 0 through 25. 0 represents A, 1 represents B, and so on. And there we go. That's what our node looks like. So let's go ahead and see how adding stuff to our trie looks like. So we're going to add in the word abs because it's only 3 characters long and I can make that fit on the screen. So the first thing we're going to do is we're going to make this our root because you have to start with the root node. So this is our root node. Its parent is null, represented by that dash over there. Occurrence is 0 because it's not the end of a word, it's just the root. And children, it starts out with everything initialized to null. So we're going to add A. So 0 represents A. So A has a parent that points to the root. Its occurrences is 0 because it's not the end of the word, and children is an array of size 26, everything initialized to null. Now we're going to add B. So 0 is A, 1 represents B. So B gets a node. The pointer of the node points to what came before it. So the pointer of the node is this node, which is represented by A because it's in element 0. Occurrences is 0 because it's not the end of the word. And children points to an array of size 26 that every element is initialized to null. Now S would be A, B, C, D all the way to S, which would end up over here at 18. The pointer points to the node that came before it. Occurrences would be 1 because it is the end of the word. And children is a pointer to array of size 26. Everything is initialized to null. So this right here is a graphical representation of, not graphical, but just a visual representation of a trie with the word ABS in it. So now that I think we've represented it the most that we can visually, let's get into some programming of how we program what this looks like. So let's go ahead and start here with our root. Let's move this screen over here. Alright, actually, we can do better than that. Let's just move this part over here. Alright, so we go ahead and we've gotten this started. So our alphabet size, we'll make it 26 because that's our alphabet. And then we have to define if we're working with uppercase or if we're working with lowercase. And here's a quick demonstration of why. Bring this guy over here. So let's go ahead and run this. So if we're dealing with lowercase, then the numerical values for A, B, C, or D are shown here. And if they're uppercase, well, if you notice, the numerical values are a little bit different. And that'll be important later. And if whether it's uppercase or lowercase doesn't matter at all, well then make everything either upper or lower. If it does matter, well then you can do a little check. You can just do is lower or is upper, and it tells you. Then you can go ahead and do your calculations from there. But all that, why this is important, that'll be shown very shortly. So go ahead and close that. Go ahead and close this. Don't need this in here anymore. Alright, so let's get programming. So right now all we have is our root. So our root, we're going to make it a struct. We're going to call you node. Well, we're not doing just the root, we're doing all nodes. So they're going to be node. And we're going to do the parent, which is going to be a pointer. Parent underscore, because I like to use underscores when I'm inside of either a class or a struct. And we'll initialize this to null pointer. And then we will do children. And children will be a pointer to an array. And array will be, the size of the array will be whatever the size of the alphabet is. And we'll initialize these to null. And I've also noticed this works if you just do it like this. But that seems scary to me, not initializing it. So we'll go ahead and if we do empty brackets, it sets everything to null. And we'll do children. No, we just did children. We'll do occurrences. Underscore, we'll initialize you to 0. And this right here is, oh, see, I still have vector there. Don't need that. This right here is what, instead of being int, another way to do it, and I'll put it in the description. I'll put a link to what I used when I was doing this as a reference, and he made it a vector of integers instead of just an int. But for what we're doing, we'll just make it int occurrences equals 0. Then every time we've reached the end of a word, it'll be incremented on that node. And this should be it. This creates This right here creates this node. Parent points to null, occurrences is 0, children is a pointer to an array. Everything is initialized to null. And then once we have either whatever character, an A, a B, or C, then a node will be put in there. So let's go ahead and start that right now. Let's do insert node. So insert node, we'll do a node pointer, and this will be our first one will be to give us our trie tree. And then we will need to know what we're adding. So we'll do a char pointer to word. And the first thing we're going to do is we're going to make a pointer. We're going to make a new pointer. We're going to call it current node that points to the tree that we're working at. The reason why we're doing this is so this way we can use current node to navigate through the tree. While whatever character in the word we're working at is not the one character that's past the end of the word. Then we go inside. I have current node that points to children. So if current node, which is this node right here, if we start at root, that points to the children, so now we're looking at here. And we'll do whatever word minus case, which is, I should have left that other one up. This is what I showed you earlier, that A equals, I think lowercase a equals 97, B equals 98. So this way, if it's lowercase a minus lowercase a, because that's our case, well then this would be 0. If the word is B minus a, well that would be 1, and so on. So if whatever element we're in is equal to a null pointer, I don't want capital, then current node points to children. Let's see. And copy that. Alright, so if whatever node we're looking in here is null, then we're going to go ahead and we're going to make that a new node. Then we're going to take that and we're going to make its parent equal current node. So we'll make a new node, we'll point the parent back to the node that it came from, and we're going to show how all this looks visually after we're done. And I think that's actually about it. Or that's it for that. Go ahead and scroll down. Let's go ahead and make this a little bit better to look at. Alright, so then what we're going to do is we're going to go ahead and move our current node. And we're going to move it to whichever element that we're in. We're going to move to the next character in the word, which will go back up into the while loop. Once we're done with everything in the while loop, then we will increment not that big crazy guy over there. We'll increment current node that points to occurrences. So this way, once we are done with the loop, which means we're just past the last character, or we're at the last character, then we'll make the node, we'll increase its occurrences by 1. So this is what it looks like to create the node. Move it down here. So this node looks like that. Occurrences, or not occurrences, but how to insert a node looks like this right here. And I think this looks good. Let's go ahead and move that out of the way. Come back over here. So let's see that code that we just did. So we'll do insert node. So we know how to create the node. So we'll move the code back over here. This is the code that we've just created. And let's get started with the code. So first thing we're going to do is we're going to insert the node. It's going to get a trie tree. This right here is our trie tree. We're going to assume we've already made a trie tree that has the root. And we're going to pass it to this function. Word, well here we'll do our word as ABS because it's only 3 characters and I can make it fit on the screen. Current node will be a pointer that points to our trie tree, so it's going to point to the root. While word does not equal this guy right here, which means the 1 character that's past the end of the word. So since it's a char pointer, it first points to the very first character. If that character minus case we're using lowercase instead of uppercase, so lowercase a minus lowercase a is equal to 0. So that's why that's nice and shaded a tad bit darker. So if whatever element we're looking at the child is equal to null pointer, which it is, then that element gets a new node. So here's a new node. The parent is pointed to null, or to a null pointer. Occurrence is 0. Child is pointed to an array of size, whatever our alphabet size is, and everything is initialized to null, or null pointers. It goes beyond this, but you can see everything's null pointers. Then we're going to take this node and make its parent point to what came before it. And then we're going to move outside the if statement. Our current node is going to move from where we were to whichever child we moved into. So our current node now moves down here. We'll increment word to the next character. So the next character is B. And move back up to evaluate our while statement. So if this character does not equal past the end of our word, then we'll move in. B minus A is equal to 1. So if current node in child, so the children of our current node, if the element 1, which is right here, which represents B, is equal to null pointer, which it is, then that element gets a new node. So the new node, the parent is null, occurrence is 0. The children points to an array of size 26, everything is null. Then we'll go ahead and we'll make the parent point to what came before it. So the parent points to what's currently the current node, what came before it. Move on, move the current node down to whichever element. So now we're at this node. Increment word to the next character. The next character is S. Let's go ahead and move, well first we'll evaluate this while statement. Then we'll, let's see. There we go. I was wondering when we moved the whole thing over here, all this code. So while S does not equal past the end, it does not. If S minus A equals null pointer, so now we'll actually move all the code so we can see S minus A is equal to 18. It is a null pointer. So we'll go ahead and make a new node there. Parent equal null pointer. Occurrences is 0, and children, or children points to an array of size 26, everything initialized to null. We'll go ahead and we'll set the parent pointing to what came before it. Move current node into whichever element we were just in. Increment word. So now we'll move our code all the way down here so we can see that now we're pointing past the end of our word, which is represented by the /0, \0. So while word, which is \0, does not equal \0, which it does. So we'll go ahead and whichever current node is, which is right over here, or the last node that we've created, we'll increment occurrences to 1. You can see it looks like that. And we're at the end of our insert node. So we'll go ahead and move that out. And this is what it visually looks like, what we've just created. That was how to create our nodes for our Trie tree and how to insert a word into our Trie tree. I'm going to make, this is going to be the end of this tutorial. I'm going to make 2 more tutorials. We still have to delete a word, we still have to search, and we still have to print. So we'll go ahead, I'll break that up into the next 2 tutorials. I hope this was helpful. If there's any way I can make these more helpful, please put it in the comments. If by any chance you're looking at this and you're already a professional and you've noticed that I'm doing things incorrectly, please by all means go ahead and put it in the comments so I don't keep doing things the wrong way. I hope this helped, and thank you very much for watching. Hope you have a good day.